All right, guys, welcome back to class. We are going to finish chapter 7 today. Um, there are a few things that I want to go over to finish the chapter with Newton's gravitation. Okay. Um, this application is what we call the design of loops in tracks. And one of the differences is that in here, you have a vertical loop. So you have a mass that is being dropped, and then you have it going around a loop like this. You can find simulations online, and I had one here. As Kepler's laws, okay, yeah. You can find some simulations where we can recreate this. Roller coasters are probably the best, but the idea is to understand why a mass or an object moves the way it does. Why it doesn't fall, or why it actually completes the loop. So, yeah, this one will be probably the best. Now let's see if you can just put a loop in there. Okay, so can I do a loop quickly? Let's see. If not, I just show you a video online. Where's the volume? So this one is probably not the best. Let's just do, that's good, but let's just do loops, simulation, physics, Centripetal 4. Now everything is online, so there should be, oh, there it is. That's easier. Okay. So you see a mass, it's dropping, then it's going up, and if it doesn't have enough energy, it's gonna fall. So we can increase the velocity. Let's see, how can I do that here? Initial, let's decrease this. So let's increase it by 2 meters. There. So now I increase the height. And the mass should make it around the loop. Yeah. So why does the mass didn't make it before, and now it basically went over it and then it continued? Because I added more energy, right? If I release a mass at a higher height, right, from a higher point, then the mass will have more potential energy. We're measuring the potential energy with respect to this line. You will let it go, and then when it reaches this loop, it has enough energy to go over it, and then it won't fall due to gravity here. It will be held. And what's holding the mass? Gravity and the centripetal force. You see, if you do a forces diagram here, or a free body diagram, there is a force going down, which is mg, but you already know from yesterday that there is also the centripetal force. That force is pointing towards the center. So the condition, so that's what we have to write here. So the condition for the mass So the condition for the mass to make it around the loop is such that the centripetal force must be equal to the force of gravity weight. So mg is equal to the centripetal force. Centripetal force, the equation is mass times centripetal acceleration, which is v squared divided by r. Right? That's v. So mass is irrelevant, as you already have seen in labs or in conservation of energy, it cancels. So gr equals to v squared. So v is the square root of gr. That's the condition. Now, how do I find v? Right? Like, what if I don't have the radius of the loop? How do I calibrate v and r? Well, if we assume there is no friction here, which is not always the case, but if we assume that there is no friction, the energy here is equal to the energy here, right? So we can review. Let's review conservation of energy. So the energy at point A is equal to the energy at point B. And this is my reference. So because I'm letting the mass go with initial speed 0, the only energy at A is the potential energy. The energy at B, however, you have to be careful, because the energy at B is potential to R and kinetic. So m g h equals to m g times 2r plus 1/2 of the mass v squared. Oh, but I already have v here. So mass cancels, and v squared is just gr. So look what I get. I get a gh is equal to 2gr plus 1/2 of gr. And gravity also cancels. So I can get a value of height. So I can theoretically find the value of the height for the roller coaster. So the mass makes it around the loop. 2r plus 1/2 r is 2.5 r. So just by making the height 2.5 times or more than that, greater than the loop, than the radius of the loop, then you know that it will go through, it will go over. That's why roller coasters, right? This one. If you haven't tried this one, you should. That's why you see how high it is. So it can actually make it when it goes all the way down. It goes loops around here. You see those loops there? That's why. Right? So they don't make those heights just to scare people. They made it so it's actually stable. What's the other one that is good? Ah, yeah. Um, That one also has a loop, right? Yeah, this one here, right? So it goes really high, and the loop is also, I mean, from this picture, it's probably not very, oh, here it is. It goes very high. So then the loops are also big, but these give you all the energy that you're going to use in all those loops, right? So that's why they are like that. And they make it even greater than that, like more than 2.5. So it's actually more safe, right? But that's why, right, roller coasters are really good applications of conservation of energy. And now you can see centripetal forces. All right. Now, that's what happens on the top. That's the condition on the top. What about what happens at the bottom? So you probably have experienced this. As the mass goes down, you feel your stomach going up. Right? That sensation is what scares people. Not the loop per se, that goes really fast. And if you close your eyes, you don't really feel it. But this one, why? What is happening there? Well, let's take a look at the forces. Let's use this. The force of gravity, mg, but you know already that when there is a mass on the ground or the floor or a surface, there is a normal. That's what you feel. That's what makes your stomach go up. That's what that's a force acting on your body. So what else? You have the centripetal force. So what's the condition at the bottom? There is a no. It's a similar condition, but here we didn't have the normal because it was just centripetal force and the value of mg. Here, the condition at the bottom is that the normal minus the force of gravity, mg, is equal to the centripetal force. All right. So what we have is this. Normal minus mg equals to the centripetal force. Now, because you are actually going down like that, right? You have this scenario where the centripetal force, you have a velocity here, a speed. You have m v squared divided by r. Oh, by the way, that's basically the force experienced by pilots when they are trying, there is a famous exam that astronauts or pilots they have to go over to in the academy, and is to fly an airplane and do loops to see their resistance. That normal can be even greater than the force of gravity, right? 2Gs, 3Gs, 4Gs. So that's basically what it is. The G force, exactly. All right. So the difference between this and the one on the top is that if we were to write an equation here, right, it will be mg minus the normal, which is 0, equals to the centripetal force, which is mv squared divided by r. Why the normal is 0? Because that's the limit, right? That's the condition for the mass to go over the loop. All right. So then we have examples of this. One was the one I showed you yesterday. And one is the following is here, this one here. A roller coaster has a mass of 500 kilograms when it's full. If the vehicle has a speed of 20 meters per second at point A, you can approximate this to have a radius of 10. What's the force of the track on the vehicle at that point? And then what's the maximum speed that I can have at point B for gravity to hold it on the track? So this is the loop there. All right. All right. So here you have the speed. Here you are being asked for the speed. So you just have to apply the condition at the bottom, the condition at the top. The condition at the bottom is that that force that they are asking you is the normal force minus the weight of the vehicle is equal to a centripetal force. That's, what is it? That's this. Okay. So radius is 10. The speed is 20. The mass is 500. So, example. Normal minus the mass is 500. So, 500 times 9.8. That's equal to centripetal force. Mass. The speed at that point was 20. And the radius was 10. So now I can find my normal, the force exerted by the track. All right, let's put it here. And let's open this. So 500 times 400 divided by 10, of course, this is 20,000. Plus 500 times, or 980 times 5, that's 4,900, right? Yeah, 4,900. So if you do the math, yep, is 24,900 newtons. That's the force that is acting on the vehicle at point A. All right, so that's the condition. Very important, you see? This. And it's easier because you are at the bottom. We're going to do a problem in a bit when it's not necessarily at the bottom, right? Because remember, the mass can be here or here. So there is also a normal force here, but it's like that or like that. So we want to talk about that as well. All right. Now the roller coaster, it continues, right? And then it's going to reach point B. And they're asking you, what is the maximum speed so the vehicle keeps moving around the loop? right? Here, when the radius is now 15. So the condition at the top, so now at B. The condition at the top is that the centripetal force is equal to the weight of the body. All right. So give me a second. While I go and do something, try to solve it. You have here, you have the centripetal force. The centripetal force, that's where you have the speed. You have the radius there. So try to find the value of the speed. Give me a couple of seconds. So square root of RG. Yeah, it's about, no, it should be more than that because it's 15 times, it should be more than 12, about 12 point something. The radius is 15, not 10. So it's the square root of approximately 150, which is 12 point what? Yeah, 12.2 meters per second. So it makes sense, right? It's lower than before because it went up. It went up from here to here. So the speed decreases, the potential energy increases, but it's enough for the car to keep going around. Okay, so that is a good example of centripetal forces acting in loops. Okay, acting on loops, sorry. I think this one is the one that you have to be more careful. So let's do another example, all right? Because roller coasters are one application. Another application that I want you guys to learn is the pendulum application. It's similar to what we did yesterday with the string, with the chain. That one is, it can be like this, but there's one that is more interesting. It has more questions. This one here, right? You have a pendulum, right? Like swinging like that. They give you the direction of the velocity there. So it says that, well, you have a pendulum with mass 0.500 or 0.5 kilograms, and it's swinging vertically, right, on a radius like this of 2 meters, as shown in this figure, all right? When the angle is 20 degrees, so when theta is 20, the speed, so they give you the speed, 8 meters per second. At this instant, you want to find the tension in the string, the tangential and radial acceleration. Radial acceleration, by the way, guys, is centripetal, okay? Radial is centripetal. Radial is on the direction of the radius. So that's the total acceleration. And then, well, we don't have to worry about it. Let's calculate this. All right. But yeah, the answer will change if you're at the lowest point. It will change because at the lowest point, the angle is not 20, right? The angle with the vertical will be 0 degrees. The angle is important. So now you are at an angle, like I was saying, right? And it's hanging on the air. So there is not really a normal per se, but there is tension there. Okay. So I'm going to draw it here. I want you guys to think. The first thing you have to do in this problem, you have to draw the forces acting on the mass. So you have the vertical, you have the pendulum like this, and it says it's moving at this instant at 8 meters per second. The mass is 0.5 or 0.500 kilograms. And they give you the, yeah, this is of 2 meters. So, okay. Gravity. And the angle is 20 degrees. Okay. I will add something to help you guys. Let's use this as the direction of the, that's your circle there. It should be all the way here, right? But this is an arc of the circle. Okay. So what forces are acting on the mass?
mg.
Yeah. So you draw it like this. What else?
Centripetal force.
Yes, but before you do that, you want to draw the tension and then, yeah, centripetal force. So tension, and on that direction, you got centripetal force. Okay. Which is a radial, right? This is the one because it's the center of the circle. All right, there. Okay. So in the previous problem, right, or example, the normal or if you were at the bottom here, that's the bottom of the trajectory, the tension and the force of gravity, the weight, are on the same line. But now because of this angle, the tension and the centripetal force are pointing towards the center, but the force of gravity is going down. And this is important. We need this. So we need to break this into components. So what you are going to do is you are going to find this component, which is on the same line as the radius, and this component, which is tangential to the radius, to the circle. This is a radial component of the weight. This is a tangential component of the weight. So here is where, well, guys, let's see your geometry there. You see this angle, right? And this is a vertical. This is all a vertical line. This is also a vertical line. So what's the angle here? What's this angle here?
Is it 20?
Yeah, parallel lines. These are corresponding angles. Okay, so you have seen this in the past. You can tell me what is the tangential component of the weight and the radial component of the weight. What will be the radial component of the weight? Okay, so
Wait, I'm confused. Which one's the radial and which one's the tangent?
this is the radial component. It should be like a line here. You see the tension is here, the centripetal force, and then you have the weight here on the same line.
Yeah. Okay. Thank you.
That's the radial and that's the tangential component.
Okay.
I have a quick question.
Mhm.
Yeah, so how it's like kind of the example that you gave yesterday, with the person swinging, like we didn't have to figure out the components
That one was
because it
because
didn't have an angle.
it didn't have an angle. It was just uh the vine was like this, and the person was swinging, and at the bottom here,
We were just trying to find that point. Okay, I got you. No problem. I was
tension,
just
and
looking.
then
I was trying to like relate it back to that problem, and I was just a bit confused, like why everything was
yeah.
going.
If you're looking at if the person was here, that's when you have to figure it out the angle. You have to know this. Yeah.
Okay, all right, thank you. That makes sense.
So now we're doing that. So that's why that's the situation here. So what's this component? That. And the tangential is all right. So how does tension, centripetal force, and this relate?
Isn't it the centripetal force is equal to the tension minus the weight?
Yes, perfect. The centripetal force is the tension on the rope minus that component of the weight. mg cosine 20. That's it. And guess what? That's the question A, the tension in the string. So tension is centripetal force plus mg cosine 20. Centripetal force, mass v square divided by radius plus mg cosine 20. Mass is 0.500, or just 0.5. V square is 8 square, 64, divided by the radius 2, plus mg cosine 20, mg times cosine of 20. All right, so anybody can do this quickly?
20.6.
20.6, perfect. There it is. See, guys? How about that? Any questions about that? That's why the whole idea with components and inclined planes are important, because they do come back a lot in different applications. This is now the pendulum application. There's more though. Find the tangential and radial acceleration. So the radial acceleration is a centripetal acceleration, okay? They're the same. They are, as you should know already, v squared divided by r. The tangential, that one is a bit tricky. I don't have to show you how to do that. But this one is easy. What's v? 8. So 8 squared, 64, divided by 2, that's 32. So that's easy for the centripetal. Is that clear so far? Yeah, okay. What about the tangential acceleration? Okay, let's show you this so you remember. The tangential acceleration is the component of acceleration parallel to this velocity. Right here. And I gave you this equation yesterday, alpha r. But alpha is normally not given in problems. The angular acceleration is a variable that sometimes they give it to you, sometimes they don't. Right? So how do you find the tangential acceleration in problems like the pendulum one that we have right now? Right? Well, we have to look at the tangential component of the velocity and the force. The velocity is going like this. But the tangential component of the force is this. Is there another force acting on this direction? Not really, right? So this guy mg sine 20, that is equal to the mass times tangential acceleration, because this is the tangential component of the force. Force tangential. Okay? So the mass doesn't matter, and I get that the tangential acceleration is g sine 20. And how much is that? We got this for a radial. This should be your tangential. Is that what you get?
Yeah.
Yep. 3.35. All right. Tangential and radial or centripetal. And lastly, how do you find the total acceleration? How do you find that? Remember? I gave you the equation for that as well. Centripetal is like this. Tangential is like this. So, and this makes 90 degrees. So how do you find the total component? What do you do?
Pythagorean theorem.
Yeah, so tangential square plus centripetal or radial square. All right? There it is. What's the answer for this? So double check and then we can go over this again, just if you have any questions. So what do you get for total?
32.17.
So 32.2 meters per second square. All right. Any questions? So forces diagram, free body diagram, definition of acceleration, centripetal and tangential, all of that matters in this type of problems. All right. We're gonna do more of this. Luckily, like I said, we have at least Monday to do like a review of some of these parameters. We have time today. But the last topic, the last application on chapter 7 is Newtonian gravitation. All right. So why do we use that? Because we can analyze the motion of planets around the sun by assuming that they travel in almost circular orbits. We know now that actually the motion of the planets is not a circle but an ellipse. What's the difference between a circle and an ellipse? Is that the sun is not really at the center. So in if we were to assume circular orbits, the sun will be at the center and planets will move at the same speed. So they will have a period because they move at the same speed. And planets that are closer or farther from the Earth will move at constant speeds as well, but also different than the ones than the Earth. Now that's true. That's true. Planets do move at different rates, depending how close or how far they are from the sun. But because the sun is not at the center, but at one of the focal points, an ellipse has two focal points, by the way, here, and the other one will be here. Uh, the farther the planet is from the sun, the slower. And you can see with this vector, you see, and this is more, now we're going more into astronomy, but you see how it's slowing down here, and then it's traveling faster at this point. That is a consequence of the ellipticity of this orbit. You see, we characterize the orbits of planets by measuring the eccentricity. The eccentricity is a ratio between C and A, C divided by A. A is the semi-major axis of the ellipse. C is the focal distance, the focal to the center. That's C. So that value for this particular planet is about 0.33. For planets like the Earth or Venus, it's actually very close to 1. So that's why we can assume that that was a confusion almost 2000. Well, that was the Greeks. Yeah, the Greeks 2000 years ago, they assumed that, well, the Earth was the center and the planets were orbiting it. But later on, they assumed that the sun was the center, the planets were orbiting it, but they assumed that the planets were orbiting in circular fashion. So the eccentricity was 0. And there are issues when you assume that. It's a nice simplification, and we can use it, by the way. We're going to use a simplification to explain some of the forces acting and the orbits of the planets, but it's not correct because when we look at the orbits of Mars, for example, and how it behaves with respect to us, then if we assume the orbits to be circles, we cannot fully explain the position of the orbits of the planets around the sun. It was Kepler, that's why it's called Kepler's laws, the one who realized that the orbits of the planets had to be ellipses. And that's important when we, for example, do the law of areas, right? A planet sweep equal areas in equal time. All right. So this basically allows you to explain that even though the planet is traveling at a faster rate here than here, the area swept by the planet here is equal to the area swept by the planet here. All right. Again, that's more astronomy than physics, but we use physics to prove this. For example, the equation or the physics that we use to prove this is the conservation of angular momentum. The conservation of angular momentum fully explained that the speed of the planet here is less than the speed of the planet here. Right? But it doesn't matter because of the distance, it covers the same area as this. Right? You will think that there's more area here, but the distance here makes up for this distance. All right. Now, that law, this, and then this, the Kepler's third law, right? That is actually just, or they were just actually not ideas, I don't like to call them like that, but they were like the introduction that Newton used to develop his theory of gravity. Because you see, when Kepler came up with this, he wasn't able to explain why a planet slows down or speeds up when it's closer to the sun. In other words, he was not able to discover the force of gravity. It was Newton that discovered that, and when he looked at the moon, he wondered why the moon is not falling towards us like the apple falls from the tree. And in reality, the moon and satellites orbiting the Earth are on free fall towards the Earth. The reason they don't fully fall is because they are in orbit around the Earth. So they are in free fall, but they are at the same point in orbit, traveling in what we know a stable orbit due to the compensation between the force of gravity and the centripetal force. That allow us to find orbital velocities of satellites or planets around the sun. Again, by assuming circular motion, circular trajectories. So the first idea that you need to know from Newton's law of gravity or Newtonian gravitation is that there is a gravitational force exerted by a planet or by a star on a planet and vice versa, which is equal to the equation that you have in front of you. G, capital G, which is even there, multiplied by the masses divided by the distance between the planets or the planets and the sun square. And keep in mind that now, and this is good because in chapter 8, we're going to be talking about this. Now we are actually considering these objects as spheres. So they have mass and radius. So they have a volume, they have a dimensions. So they are rigid bodies. And you know what happens when we're talking about rigid bodies, right? So this is the universal law of gravity. And we can use this equation to, for example, find the force between the Earth and the sun. And we can use it to find force equals to mass times acceleration. So I can use it to find the acceleration of, or the centripetal acceleration of the Earth orbiting the sun, right? Now, here is an example of free fall G at various altitudes. So you probably have heard that as the farther you go from the Earth, the lower the value of gravity, right? The value of gravity 9.8, 9.81 is when we're on the surface, and it becomes a little bit greater when we're at the equator, closer to the center of the Earth. So the closer we are towards the center, the higher the value of gravity. The more we escape from like the more we are away from the ground, the lower the value of gravity. And I can actually explain that with the equation. Why is that? You have here the sun. And you have the Earth. So there is a force acting from the center of the sun to the Earth, and from the Earth to the sun. So people wonder, right? Action, reaction. Same magnitude, different directions. So Let's erase a vector notation. These are magnitudes. So magnitudes are the same. Vectors are not the same because different directions. Center of the sun, center of the earth. And you know that force is G, mass of the sun, mass of the earth, divided by the distance between them squared. Just so you know, guys, approximately in average, the distance between the earth and the sun the sun and the earth is about 150 million kilometers. 1 AU, 1 astronomical unit. Now, the earth is in free fall towards the sun. And the sun is also, in theory, right, in free fall towards the earth. So why doesn't the sun accelerate towards the earth like the earth is doing around the sun? It's the same idea as the apple falling from the tree. If you have the ground here and you have an apple, the apple and the earth, there is a force in between these two. But the apple has mass m, and this is the mass of the earth. Because the mass of the apple is much, much less than the mass of the earth, because the force is the same for the apple and the earth. You see acceleration here, which we know is gravity, right? We see the acceleration of gravity of the apple towards the tree, but we don't see it. We don't see the acceleration of the earth towards the apple. There is a force, and technically the earth moves towards the apple, but it's negligible because of this. So the force is the same, the acceleration is not. So then here, if I want to find the acceleration of the sun towards the earth, you can just say this equal to mass of the sun cancels. And what is this? This. So Newton realized that the acceleration of gravity of the earth can be calculated by the G constant, the mass of the earth, times the radius of the earth square. Now, believe it or not, the radius of the earth was calculated already by then. You can watch this video. 2,000 years ago, this mathematician discovered the radius of the earth by using sticks. You probably have read about this. The shadows between Alexandria and Siena. So they discovered the circumference of the earth, and with that they discovered the radius. So he knew that. And then the mass of the earth, you can find it by using the orbit of the earth around the sun. So the period of the orbit. So if we know the mass of the earth and the radius of the earth, let's use this equation so you can see how you use it to find the value of gravity. Okay. Now let's find the values of the mass and the earth. Okay. Mass of the earth is about 6 times 10 to the 24 kilograms. So that's the mass of the earth. So mass of the earth is 5.972 times 10 to the 24 kilograms. The radius of the Earth is about 6,400 kilometers. But again, let's find a more accurate value. 6,371. Okay. All right. Let's see what we get if we use this equation. Gravity of the Earth is the G value, the capital G, which is this 6.673 times 10 to the negative 11. 6.673 times 10 to the negative 11. G, mass of the Earth, divided by the radius square. But this is in kilometers. 6,371 times 1,000 to change it to meters square. Okay. You know how you be careful with the calculator. The way I do this is 24 minus 11, the exponents, minus 10 to the 6 here. So 10 to the 7. I here have this times this divided by this. So 6.673 times 5.972 divided by 6,371. Oh, I didn't square this. Silly. You have to square this as well. So, okay, divide by 6,371 again. All right, so I get 9.81 times 10 to the negative 7. Yeah. So, they cancel, and look what we get. 9.81 meters per second square. So, we can prove with Newton's law of gravity that the value of gravity on the Earth is that. All right. So the gravitational force, G m over radius square, can be used as well to find the force acting on rockets or satellites, right? If you have, for example, our planet, you have the Earth, and you have a satellite orbiting the Earth, right? In circular, semi-circular, almost circular fashion, right? The satellite is at some height over the surface of the Earth. So there is a distance between the satellite and the center of the Earth. So how does the satellite moves? How do we know the speed of the satellite and the acceleration of the satellite around the Earth? By using this. You see, this force is also the force between the satellite and the planet. Big M is the mass of the Earth, M is the mass of the satellite. So I can make this equals to mass times acceleration of the satellite. But wait a second though. What type of acceleration is the one on the satellite? Is centripetal acceleration. And that is mass, the speed of the satellite square, divided by not just r, but r plus h. So mass of the satellite is irrelevant. You need only if you know that g, of course, the mass of the Earth and this distance, which goes here, but this r is r plus h. So if you know the altitude of how far the satellite is from the ground, and you know the radius of the Earth, you know the speed of the satellite. All right. So let's find that. In fact, let's do a real one. It's about 420 kilometers. Yeah, 400 kilometers. So the ISS is at about 400 kilometers above the surface of the Earth. Let's find the speed of the satellite, and also let's find the period of its orbit. All right. And there is a problem like that in the book. So let's show you how to do this. So 400 kilometers, h is 400 kilometers. That's the altitude of the satellite. That's this. So for the satellite to be orbiting the Earth, the centripetal, the gravitational force between the Earth and the ISS or the satellite has to be equal to the centripetal force. There you are. And look, I don't know the mass of the ISS. I only know how far it is. Just by knowing how far it is, I can find this. I don't need a mass of the satellite. All of these cancels with one of these. So my V is the square root of the G value, the gravitational constant, the mass of the Earth divided by radius of the Earth plus the height of the satellite. So the only thing you guys have to be careful is when you substitute the values. All right? G is this. So there. In fact, I want to let you guys do this now. So I'm going to put the numbers here and you guys find the value. This was 6,372, 71 plus 400, 6,771 times 10 to the 3. Square root of that. You are finding the orbital velocity of the ISS. All right. What do you get?
224. What? Okay, how do I even say this? 24261.
525? That high?
No, no, no.
Did
24261.
you take the square root?
Yeah.
Maybe, because that's in meters per second. Let's see. 6.673 times 5.972 divided by 6771 square root. I get 7,671. Did anybody get the same 7,000 or 24,000 or 242,000?
Wait, I got that. I did the bottom one wrong. The divided. I got
So
that.
7,000,
Yeah.
671.7 meters per second. This is why for orbital velocities of satellites or even planets, we write this in kilometers per second. How do we write this in kilometers per second? We just divide this number by 1,000. It will give us 7.67 in free suffix there, kilometers per second. That is the orbital speed of the ISS. Okay? Yeah. There you are. There you are, 6.67 kilometers per second. I mean, it's all in the physics, right? I'm not making anything up. I'm just proving you guys everything that we use in satellites or planetary motion in this case, because we can do the same for planets. Now, that's just the orbital velocity. What about the period? Who remembers what's the period of an orbit? What is the definition of period? Period is the time it takes for a mass to orbit, or period is a time of one revolution. In planetary motion, it will be the time it takes for a planet to orbit the sun once, or in satellites, the time it takes for a satellite like the ISS to orbit the Earth. So, period is basically the circumference of the Earth, of the trajectory, not the Earth, divided by the speed. Okay, that's very important, guys. Period is the circumference of the orbit What's the equation for circumference, by the way? What's the equation for circumference? In 2 pi r, right?
2 pi r.
2 pi, what will be R? Let's go to the problem. R is this whole thing because that's the ISS. ISS is doing all this. So let's do it better. So the ISS, right? Let's do two shapes. The Earth is like this. The ISS is like this. So the total R is R plus H. Radius of the Earth plus the height. So 2 pi R plus H divided by V. You know what? Let's use V kilometers per second because look what's going to happen. I can leave this in kilometers. Radius of the Earth is 6,371. The height is 400, so 6,771 kilometers. And then here we have 7.67 kilometers per second. So my period will be in seconds because kilometers counts. Okay, so what do you get here? Two pi times this divided by this.
$5,546.
Yeah, that's more accurate because I put 2 pi. Okay, so 5,546 seconds. All right, so it's a good number, but how about we put this in hours? How many hours is this? How do you go from seconds to hours?
Divide by 3,600.
Yeah,
Got 1.54.
1.54 hours. Amazing, right? The period of the orbit of the ISS. So we found the period, we found the speed, right? By using gravitational force and centripetal force. Any questions? So based on what we have discussed, the apple, the planets, which ones of these are true? I explained that with the apple. For B and C are false. Yes, right? For Yeah. Only A is correct. Why? Like I said, when an apple is falling towards the ground, the force exerted on the earth is the same as the force exerted on the earth to the ball on the earth, due to the action reaction. But because the masses are different, the accelerations are different. The acceleration on the ball is g. The acceleration on the earth is almost zero, because it's the same force divided by a much larger mass. That's why we don't feel the earth moving. The magnitude of the force is not that kind of it. So it's only A. This is how they measure gravity. All right, I believe this is a Cavendish apparatus. Yep, it is. That's how they measure the value of capital G. This capital G, by the way, is the gravitational constant. That was theoretically found by Newton and is considered one of the fundamental constants in nature. Basically, the universe moves the way it does. Or one of the reasons we have solar systems, planets, stars, and galaxies, right, is because of this. If this G value was slightly different, we probably, most likely, wouldn't be here, because this governs the force of the gravitational force. If the gravitational force was different, then the planetary motion will be different, the orbits will be different, and so on. All right. And then we have this gravitational potential energy revised, right? Remember the MGH? So we can find the value of the potential energy as, for example, an object is h above the ground, like you see here, the Earth, radius of the Earth. If we use the center of the Earth, so this is the thing though. When we talk about potential energy in problems, right? I always told you have to look at the reference. And the reference is normally the ground. But in a more realistic setting, right, for asteroids, planets, or satellites, right, the reference is going to be the center of the Earth, because we are above the ground. We are radius units above the ground, above the from the center, right? We are on the surface of the Earth, so we are 6,400 kilometers from the center of the Earth. So because of that distance respect to the center of the Earth, there is potential or gravitational potential energy here. And as we go farther, the value of gravity decreases, the value of this gravitational potential energy, the magnitude, decreases. So if I want to do the difference between potential energy on 2 minus potential energy on 1, I get this. So where does this equation come from? This looks like a gravitational force. If you have taken calculus, you can easily prove that. I'm just going to show you the equation. The gravitational force is equal to G m1, or mass of m1 m over radius square. If you want to find the potential energy, the gravitational potential energy from a given force, radial force in this case, that's just the integral of the force respect to r. It's a dot product. So if you do the integration, you get potential energy, gravitational, negative G M1 M over R. That's where it comes from. The negative is interesting because you know that, and let's take a look at this. The more negative a number, the less potential energy, right? So the potential energy at this point is going to be zero. The potential energy here is, or sorry, it's going to be the maximum. As you go farther, your potential energy is increasing. Why is it increasing? Because it's less negative. All right. That's why P2 minus P1 is a positive number. This fraction, if I take the absolute value, this fraction is less than this fraction, or is greater than this, is less than this fraction, sorry. Yeah, this fraction is less than this. So you will say, oh, so energy here is less than energy here. But the negative is the difference, though. This is a less negative fraction than this. And you know from the number line, the closer to zero from negative numbers, the greater it is, right? -2 is greater than -4. So gravitationally speaking, the farther we are from a planet, the less or the greater potential energy we have. All right? That's why when we are approaching a planet, right, magnitude-wise, the gravitational potential energy increases. Yeah, magnitude-wise, it becomes more negative. That negative is just a situation. It's just the mass approaching a planet. Okay? So value-wise, it makes sense. As you are farther from a planet, your potential energy, magnitude-wise, is less because the gravitational pull is also less. As you get closer to the planet, the gravitational pull is greater, so the potential energy is greater, magnitude-wise. All right? So if we make this h very, very small, then basically it's just, this equation is just G mass of the Earth mass h over RE times RE squared. And we know that G M over RE squared, that's the value of gravity. So at the surface, when h is basically zero or close to zero, the value of gravity is Gm over R squared. That's why we define it as mgh. Here it is. So we are basically proving the mgh formula using potential gravitational energy, which is defined, as I said, like this. So you go from one point to another point. Okay. So at the end of the day, the major equation is this. Well, you already know this, right? So let's write down here what you need to know. Potential energy, where R is the distance between the objects. The gravitational force is here. And the value of gravity for any planet now is G mass of the planet over radius of the planet square. So let's label this. This is the radius. This is distance. Different. Okay. So gravity, we already use it to find the value of gravity, right? Here. We have used gravitational forces. We found the speed of a satellite, the orbital velocity of a satellite. We found the period. What about the energy? When do we use energy? We can use it to understand rocket launching and escape velocity. You see, how do engineers know what should be the escape velocity of a rocket on Earth? Like, how do we know how to do this? And you may think it's simple, but no, it took us several years to actually understand and correctly do this, right? So, how does a rocket escape Earth gravitational pull, gravitational field? Oh, yeah, that's one thing, right? Now we can talk about gravitational fields, right? It's a property of a planet, right? The gravitational pull, gravitational field is due to the size of the planet and the mass of the planet. Anyway, we have the ground and you have a rocket. How do we know how fast these guys has to be to escape Earth? Well, we use the conservation of energy. If you think about it, when the rocket is launched, it gains kinetic energy. This kinetic energy plus the potential energy due to gravity, Earth, has to be equal to 0 so the rocket can escape the Earth. So kinetic energy of the rocket is the mass of the rocket. 1/2 mv square plus the gravitational energy due to gravity, that's this, plus minus g mass of the Earth, mass of the rocket, divided by, if you're on the ground, if you're on the surface of the planet, this distance is just the radius of the Earth. That has to be equal to 0. All right. So 1/2 mv square is g m m over radius of the Earth square. Mass cancels. So the escape velocity, that's v, is the square root of 2g mass of the Earth over radius of the Earth square. Or you can just say square root of 2g mass of the Earth all divided by radius of the Earth. So we can find, let's find it as a exercise. Let's find the escape velocity for the Earth. To what's G? 6.671 times 10 to a negative 11 times the mass of the Earth. Oh, yeah, yeah. 5.972 times 10 to a 24. Square root of all that divided by the radius of the Earth, 6,371 kilometers, so 10 to a 3. Find it in kilometers per second. All right, guys. Try to do the math. Ah, very good. Yeah. No, wait. In kilometers per second. I told in kilometers per second. Come on. What's that in kilometers per second? You got it. Come on. You have to be quick. So 11.2. Let's divide by 1,000. 11.2 kilometers per second. All right. When I teach astronomy and the students are like, oh, they think it's easy. This took years to master. I think I told you to watch this movie. And let's actually watch the scene that I like about this movie. Share. Oh, there it is.
Stand. Let's go. Back in your seats, Mr. Hancock.
Okay.
Goes for you too, Mr. Wilson. Miss Riley, what's going on in here?
They didn't start that fire, Mr. Turner.
In the first place, you are not a member of this classroom.
Neither are you, Mr. Turner. Why don't you let the boy defend himself?
And in the second place, this rocket proves nothing. You've already admitted having lost a number of your rockets. You cannot prove conclusively that another one of them didn't start that fire.
Yes, I can.
Oh. Are we to conclude, Mr. Hickam, that since leaving school, you've not only become an expert in rocket science, but in the field of trigonometry?
I didn't say that. I was
Obviously, you learned more in the coal mines than you did in high school.
Let the boy talk. Go ahead, home.
Now, the fire was near Welsh, just under 3 miles from our launch pad. And at the time of the fire, the best that we could do was 1.2 miles, which is exactly where we found that rocket, Mr. Turner. See, Mr. Turner, that rocket fell for about 14 seconds, which means that it flew to an altitude of 3,000 feet. According to the equation, S equals 1/2 AT squared, where S is the altitude A is the gravity constant of 32, and T is the time it took for that rock to come back down. Velocity equals acceleration times time. Well, are you following this, Mr. Turner?
All right, we're all duly impressed. But do you mind?
So okay, that's one. The movie also shows you how they eventually as you can see in this scene, how they launch rockets, right? The other movie that you guys should watch, it's more related to NASA and stuff, is uh this one. So in this movie, right, they show you all the math behind, well, basically what we just did. I don't know if I have any scene of this movie somewhere, but they show you the math behind rocket launching and planetary motion. Maybe you can see some of that kind of here, right? What I'm showing you right now is kind of more simple. As I said, the orbits are not really circles, are ellipses. So for example, here they're trying to explain conic, like the trajectory, how it can change depending on the velocity, all right? And I always tell students in school, look how math used to be done back then. It used to be done in whiteboard, on blackboards with, maybe that's why our understanding was better, but that's a topic for another day. So if you can watch that movie and this movie, right? Maybe it will inspire you, or it will show you what inspired people like me to pursue physics, astronomy, and science in general. All right, because this value is basically the value of the escape velocity of Earth. Yeah. All right. And it changes for a planet. And how interesting, right? Escape velocity, orbital velocity. So the orbital velocity is less than the escape velocity. And by the way, guys, as an assignment, right? Or maybe you already know, what's the escape velocity for the event horizon of a black hole? If you are on the event horizon, on the edge of a black hole, what's the escape velocity? Don't Google it. Think. Why do we call it black holes?
Oh, I just
Nobody
thought
knows,
about it.
really?
Wouldn't it be the speed of light? Does that make sense? I just
Yes.
thought about it.
Very good. Yeah, speed of light. So if you replace this value here, c equals to that, guess what you will get here? You will get if you know the mass of a black hole, guess what you will here? You will get what you know as the Schwarzschild radius. The Schwarzschild radius, if I can speak the there it is. The Schwarzschild radius is the size of an object where gravity is trapped by light. And there is your equation. I don't know if you guys can see it. There. Beautiful. Right? Anyway, I want to give you guys 10 minutes to prepare for the quiz. Monday, we're going to finish. I mean, we're almost done with chapter 7. You can start doing all chapter 7 homework. On Monday, I will do more problems on gravitation and start talking about rigid bodies and chapter 8. Remember that for the exam in next week, you're going to have chapter 6, chapter 7, and part of chapter 8. And I'm not gonna lie, I'm probably gonna finish chapter 8 next week and start with chapter 9. But I'm gonna just test you a bit of chapter 8. But all of this is gonna be on the exam next week. All right. So this class has been recorded, so take 10 minutes to prepare. And we start with exam.